Today we're going to tear down the iJoy Rotator, a swiveling surge protector. 900 joules protection. It has two LED lights. As a matter of fact, it has two bright blue LED lights, so bright I had to put some tape over them. But they don't say anything useful like power and surge protector still working. They're just two lights. It has 6 total plugs. There's 3 on the side and 3 here. If you don't want them in the front, they do rotate. Now, this thing takes up an entire outlet, and it's required to have a full outlet. It has that plug there. So it's taken 2 outlets to 6 outlets. Now this guy is not UL listed, but it says it conforms to UL ratings, and it has an Intertech listing, so it's kind of the cheaper rating agency. Let's open it up, see what it looks like inside. It says it's rated to a full 1800 watts. I'm not sure if I'd want to run a space heater through something like this, though. So it looks like opening it up is going to be as simple as taking out these 4 Phillips screws. With those 4 screws removed, you start to see cracks here. I was worried these little guys here might be glued in, but it looks like they'll just pull out, so it does look like the screws are the only thing you have to pull out to get this thing to come apart. And when you do that, you have the outlets over here, the swivel outlets here. They are connected by good sized wires, or at least the insulation is thick. You have your single plug in there, and your circuit board, which has the surge suppression and the LED lights. Alright, we have 2 more Phillips screws there and there for this circuit board. Alright, it's got 3 metal oxide varistors in there, those blue guys. It's using some heat shrink tubing to hold something against them, maybe a sensor. There's a spot for a 4th metal oxide varistor that is not populated. So assuming each of these does 300 joules, and that's your 900 joules on the box, it's possible they use this same circuit board for a 1200 joule version by populating that slot there. The rotator assembly seems to be sealed or ultrasonically welded or glued, so I'm not going to be able to open that without breaking things. But this guy here, I can take these 4 screws out and evaluate the connectors here. Alright, pretty typical stamped metal construction here. Probably not as nice as you'd find in a UL listed outlet. So over time, if you inserted and pulled out receptacles a lot, these could start getting loose and have high resistance connections. But if you're plugging something in a couple of times and it feels solid, it's probably making a pretty good electrical connection. So good enough for this type of thing, I would say. Alright, I cut the shrink tubing off of one of these guys, and on this guy here there's 2 of the MOVs with the component between them, and this guy, this one over here, that spot for MOV4 is not populated, so there's only 1. It's labeled F2, so I'm assuming this guy in the middle is fuse 1. I'm assuming this is a fuse. I'm not 100% sure on that, but it, given the F indicator on the circuit board and kind of where it's located, I'm assuming that's a fuse. I believe the shrink wrap tubing is mostly to keep these electrical connections insulated from stuff touching it accidentally. So I'm going to be putting some of my own back on that when I put this back together. But it doesn't appear to be directly connected or sensing the MOV. It just happens to be in the same general area, and so they're covering it all with that heat shrink tubing and using these guys, the circular nature on the bottom there, to hold that heat shrink tubing in place. I went ahead and reverse engineered the schematic looking at the single-sided circuit board and the components. I am not an electrical engineer, so what I'm about to tell you, take with a grain of salt, but this is my best understanding of how this circuit works. It's connected to the mains. You have an AC source, you have a hot leg here, and the neutral leg there. Now, one thing I want to point out is that these 6 outlets are connected at the end here. So this circuit does not interrupt power to the outlets at all. So the power goes, the ground, the hot, and the neutral go directly from these 3 pins to these outlets. So even if everything on this circuit board blows up, as long as those solder connections don't melt, you're going to get power passed through regardless. But what this circuit does is act as a surge suppressor and have two blinking lights. Or actually, hopefully they're not blinking. So we have 3 metal oxide varistors. 2 of them are connected between the neutral leg and the hot leg via this fuse. I'm assuming it's a fuse. It looks like a fuse. It's labeled F1. It measures 0.0 ohms resistance, so I'm pretty sure it's a fuse between hot and neutral. And that's where I'd expect to see a metal oxide varistor as a surge suppressor. Basically what these guys do is they have high resistance at normal 120 volt current voltage. If the voltage goes too high, because you have a surge, they start conducting power, and that will clamp the voltage and lower the voltage on the hot line. Now, all of these guys are just connected through a PCB trace. There's also this 9.6 mega ohm resistor that holds that center point down to the neutral if there's nothing else holding it up. Now, fuse 1 is very low resistance, so by default, this center point is going to be held up at whatever hot is. I'm going to talk about this kind of like it's a DC circuit. Keep in mind that the hot is going up and down in both directions around the neutral because it's AC, but whatever. So essentially, if you get a surge, these guys start conducting current through the fuse. Hopefully that clamps the surge, protects everything connected to this guy, and you don't have to worry about it anymore. Now, the fuse is there so that these guys don't blow up, because if these guys conduct too much current, they will break open and open shorted, or even worse, they'll fuse closed and start heating up and eventually burst into flames, or at least do a lot of sparking until they open. So this fuse is designed to keep these guys from having a thermal event. So if these guys conduct enough current so that the fuse breaks, then interesting things happen to this circuit. Because if this fuse isn't here anymore, that means that this guy here is being held to neutral with this 9.6 mega ohm resistor. And that resistor there's there just in case these guys have broken at the same time that guy breaks. 9.6 mega ohm is never going to conduct much current. It's never going to fuse. It's always going to be there essentially. So this guy, if it goes down to neutral, that has an effect on a couple of LEDs. All right. So LED 2 is connected through a diode and this resistor over here up to that guy. Now the interesting thing is it's connected to this transistor and it's being connected to the neutral. So if that transistor is conducting, this guy won't turn on. And that guy's conducting when this guy here is high. Now that guy won't be high normally because fuse 2 is pulling this down to ground. So if this metal oxide varistor is not conducting and this fuse is conducting, this LED 2 is going to be powered through that 46K resistor, this diode and so forth, assuming all these guys are there. So if these guys go out, this guy's going to turn off, but this guy might also turn off if this guy goes out. Now this guy over here, the LED 1, it's not controlled by the transistor. It's going right to there. Alright, so let's say this fuse blows because MOV3 is conducting. MO3 is still conducting. It's bringing this guy here high. And what that's going to do is this control signal that goes to the base of that transistor is going to turn on high. And this guy will conduct to neutral, so LED 2 will turn off. So if fuse 2 goes out, LED 2 goes out. Now if fuse 1 goes out, both of these guys will go out. So you have, if this MOV3 is conducting current and that fuse dies, one of your lights goes out. If these guys conduct enough current so that fuse dies, both of the lights go out. So essentially these lights are just saying, hey, are these fuses still intact? And if the fuses are still intact, presumably the MOVs are still intact, and you're still successfully clamping current. Now there's this questionable, not implemented MOV4. So this guy is in the circuit, but it's not actually populated in the circuit board. There's an empty spot there. And that would basically say, hey, we're clamping not only to ground here, but also clamping neutral to ground, or neutral and hot together. So that would add extra clamping. I think the reason this isn't in there is that you'll have no fuse in that particular path. And so they basically said, well, wait a second, if this fuse blows, these two guys can conduct a whole bunch of current until one of them bursts into flame. So you have to take one of them out. And they took this one out because the fuse goes to ground, so this has a hot to ground as a useful clamping feature. And so basically, I think that might be a mistake in the design that maybe would keep this circuit board from passing the certifications. And so to get that to pass, they said, well, we're not going to populate this guy so that if this fuse goes out, this guy's no longer connected to anything that passes current through it. Now there's also this 2.2 mega ohm resistor here, so we don't have to worry about current flowing through between those two things just because you have a really large ohm resistor there. Alright, so the circuit looks like it's a pretty good surge suppressor, at least as good as any other standard simple surge suppressor that uses MOVs. The outlets, quality-wise, is reasonable. I wouldn't run a space heater through this, but you know, just for any type of reasonable usage or intermittent usage of high current, it should be fine. You know, so I think this is a reasonable thing to have in your house, not worry about catching on fire or anything like that. You know, and I'm happy enough with it to put it into use. Now I do have complaints about these LEDs, mainly that they're bright blue. I'd much prefer to have red LEDs or less bright LEDs, and there are things you could do about that. You know, so these LEDs, the brightness is the amount of current going through it, so these 46K resistors, if I replace those 46K resistors with 100K resistors, these LEDs here are going to get a lot dimmer. Or I could replace the LEDs with a red LED if I didn't like the super bright blue. The problem with that is that the blues might take more current than the reds, and so you definitely want to replace those resistors if you're putting in a lower current LED, otherwise the LEDs might burn up if they're getting too much current.